We have all heard of breeder reactors, but what does the term breeder reactor actually mean? A breeder reactor is one in which more fissile material is generated than is used. It seems like breeder reactors are constantly in the news, especially with the recent discussions on developing countries' nuclear programs such as Iran. Nuclear proliferation has been a big topic these days within the United Nations and under the Obama administration. Breeder reactors can be used to produce weapons-grade plutonium or uranium. That is, the natural byproducts of the fission process and neutron absorption creates radioactive materials that can be used in nuclear weapons. Not all breeder reactors produce materials for nuclear weapons. To make a practical nuclear bomb from a thorium reactor's byproducts. According to Alvin Radowski, designer of the world's first full-scale atomic electric power plant, a thorium reactor's plutonium production rate will be less than 2% of that of a standard reactor, and the plutonium's isotopic content would make it unsuitable for a nuclear detonation. Thorium reactors naturally function as a type of breeder reactor that produces usable fuel for future nuclear power generation. In the thorium cycle, fuel is formed when thorium-232 captures a neutron to become thorium-233. This normally emits an electron and an antineutrino by beta- decay to become protactinium-233. This process continues as another electron and antineutrino are emitted by a second beta- decay, uranium-233. To understand the importance of this, we must first look at how nuclear reaction is started in a thorium reactor. Unlike natural uranium, natural thorium contains only trace amounts of fissile material, such as thorium-231, which are insufficient to initiate a nuclear chain reaction. This requires the addition of some other fissile material, which means another neutron source is necessary to initiate the fuel cycle for a sustained neutron reaction. The only fissile options for a thorium reactor are uranium-233, uranium-235, or plutonium-239, all of which are difficult to supply. Thermal breeding with thorium requires that the neutron population in the reactors has to be very good. This requires that there is a low amount of neutron leakage and a low amount of resonance absorption. This can be attained by the use of a reflector to scatter neutrons back into the core, resulting in lower net neutron losses, which is a feature common to most uranium-fueled reactors. The cross-section for absorption in thorium is much smaller than that of uranium, and will therefore have fewer occurrences of resonance absorption. In addition, fissile material can be bred using slow neutrons, which also tends to result in less neutron leakage due to the shorter thermal diffusion length, resulting in a higher neutron population within the reactor. These three things combined lead to the ability of a thorium-fueled reactor to function as a breeder reactor. The possibility to breed fissile material in slow neutron systems is a unique feature for thorium-based fuels and is not possible with uranium fuels. Another distinct option for using thorium is a fertile matrix for fuels containing plutonium that serves as the fissile driver while being consumed, and even other transuranic elements. In a thorium-fueled reactor, thorium-232 absorbs neutrons, which will produce uranium-233. This is very similar to the process in uranium breeder reactors, where fertile uranium-238 absorbs neutrons to form fissile plutonium-239. Depending on the design of the reactor and fuel cycle, the generated uranium-233 can remain in the reactor and can fission to produce energy, or it can be chemically separated from the used nuclear fuel and formed into new nuclear fuel. This would result in a mixed fuel system. Reactor operators would allow a batch of fuel rod to sustain a reactor for about 5 years, roughly the same as with current reactor designs utilizing uranium fuel. The fuel would then cool for a few years while the shorter-living products decay, and would be reprocessed over another year, mixing actinide waste with more thorium before being put back in a reactor. This almost entirely eliminates the need for any new fissile material to be added to start the neutron chain reaction, and thus relies entirely on thorium. It also solves the problem of storage of nuclear waste in more ways than one. It produces little to no waste that requires years of long-term storage, and it can actually use some of that waste that is currently being stored around the world as it slowly decays. There are approximately 430 operational reactors in the world that require disposal of waste. With the closing of the Yucca Mountain Waste Site project in the United States is struggling to find places to store our spent material, as well as the United Kingdom. Long-term waste storage can be eliminated by mixing nuclear waste actinides with thorium. With the past, it has proven thorium is a credible option. Many projects around the world focusing on thorium, which was once thought to be a dead fuel source for nuclear power. The fact that there is about 4 times as much thorium available in the world compared to uranium, and the need to reduce the amount of spent fuel that is being stored, it is clear that we cannot and are not ignoring the vast possibilities of thorium-based reactors. There are several different types of reactor designs currently in the research and development stage. The Department of Energy and Nuclear Regulatory Commission have identified the following advanced reactor designs that are non-light water reactors, some of them being capable of using thorium as a fuel. The gas-cooled fast reactor, the lead-cooled fast reactor, the molten salt reactor, sodium-cooled fast reactor, and the supercritical water-cooled reactor. These are being developed all over the world, and some are even operational outside of the United States. The Nuclear Regulatory Commission anticipates that they could receive licensing applications within the next decade for non-light water reactors. The following are the most likely to be implemented in the next decade based on continued discussions with the Nuclear Regulatory Commission. The gas-cooled fast reactor. The main characteristics of the gas-cooled fast reactor are fissile self-sufficient cores with fast neutron spectrum, robust refractory fuel, high operating temperature, high efficiency electricity production, energy conversion with a gas turbine and full actinide recycling possibly associated with an integrated on-site fuel reprocessing facility. A technology demonstration reactor needed to qualify key technologies could be put into operation by 2020. Lead-cooled fast reactor. The lead-cooled fast reactor system is characterized by a fast neutron spectrum and a closed fuel cycle with full actinide recycling, possibly in a central or regional fuel cycle facility. The coolant could be either lead or lead bismuth. The lead-cooled fast reactor can be operated as a breeder, a burner of actinides from spent light water reactor fuel, or a burner breeder using thorium. The lead-cooled fast reactor may be deployable by 2025. The molten salt reactor system embodies the very special features of a liquid fuel. Molten salt reactor concepts, which can be used as efficient burners of transuranic elements from spent light water reactor fuel, have also a breeding capability in any kind of neutron spectrum, ranging from thermal, with a thorium-based fuel cycle, to fast, with a uranium or plutonium fuel cycle. Whether configured for burning or breeding, molten salt reactors have considerable promise for the minimization of radiotoxic nuclear waste. The majority of the research and application of test reactors consists of the molten salt design, as this seems to be the safest way to use thorium and still obtain the benefits of a longer fuel cycle added by breeding and reduced waste. These advantages are reduced when thorium is used as a fuel in traditional pressurized light water reactors. The molten salt reactor design has been proven, and a few countries have used thorium in a pressurized water reactor, making these the 2 most likely uses in the near future. It's not certain whether or not the future of nuclear power will contain thorium-fueled reactors. However, it is apparent that there is a strong desire from companies within the United States and around the world for designing a new generation of nuclear reactors. The Nuclear Regulatory Commission has adapted their policy for advanced reactor licensing and has spent a countless amount of time developing policies for licensing of advanced reactors, changes in safety analysis, analyzing the shipping, receiving, and storage of nuclear fuel and waste. They have prepared themselves for whatever the nuclear industry brings them as we move forward, and they welcome the change.